So we'll get started with functions of several variables. So there's two types, roughly, that we can talk about, and it just has to do with what the output of the function is. So I'm going to start out with the simplest one, which is a scalar valued function. And a scalar valued function just takes values in the real number. So you put in, if it's of several variables, 2 or more inputs, and you get one number out. And so I'm going to call that a scalar valued function. And the notation I'm going to use for that is f, that's the name of my function, from Rn into R. So Rn just means that there are n real numbers that are taken as inputs. So this is a function of n variables. And the output is a real number, so it's a single variable output, a scalar function. And so you can think of that just as this. So I have inputs x1, x2, up to xn. Each one of the x's is a real number, and then the output y is a real number. And so the example I'm going to use for this week's lectures is Black-Scholes pricing formula for a European call option. And so hopefully when we look at this with all of its pieces finally, it's going to sort of become more apparent why we had to spend so much time learning how to take derivatives of little indefinite integrals, things like that, product rule, chain rule, and so on. So the inputs for this formula are going to be S, which is the price of the stock, sigma, which is the volatility of the stock, K is the strike price. So this is, what I'm going to be able to get for my, if I decide to exercise my option in the future. R is the risk-free interest rate. So that's risk-free interest rate just on money. T is the maturity. And this is the way to think about capital T, and there'll be a little t somewhere here too. They're both dates. So, this could be next Tuesday, and little t, generally, we're going to think of that as today. Oops. And then Q is the continuous dividend rate. If the asset pays dividends, then you want to take those dividends and figure out what the continuous rate would be. And Q is going to represent that number. And then this is the formula. So generally, the inputs, you think of it as a function with two main inputs. So the price of the asset, S, and then the current time, T. And generally, you can almost think of this as one input, because at a certain time, like right now, I can look at the market and see what the price of the asset is. So these are sort of tied together in a certain sense. And so the formula then is S times e to the minus q, capital T minus little t. And so this is where it becomes important to think of the t's as dates. So if I say next Tuesday is capital T, and right now is little t, so that would be 8 days in the future. So when I do capital T next Tuesday minus today, that's going to give me 8. So this quantity, capital T minus little t, you can think about that as the time left until maturity. And as time moves forward, that's actually getting shorter. And then you can see that this formula is going to simplify a bit too. If you have a non-dividend paying asset, this Q is just going to be 0. And so you'll have e to the 0, and this whole piece that I have highlighted will disappear. It'll just become 1. So I'm going to multiply that times phi, and remember phi was this function we defined as the integral of the standard normal density from minus infinity up to its argument, so this value here. So phi of d1 of st, so d1 is going to be another function that we have to evaluate. And then I'm going to subtract k times, so here r is the interest rate, the risk-free interest rate, times the time left until maturity, times phi again, and now we have another function, d2 of st. And the form of d1 and d2 are down here, so I have to wait till my slide disappears. So they're not exactly simple. So the reason we want to write this as phi of d1 and phi of d2 is just if I start plugging this whole expression into these parentheses, the thing gets quite unwieldy. And then d2 is just equal to d1 minus sigma times the square root of capital T minus little t. And if you write down what that looks like, if you plug in this formula on the left for d1, all that ends up changing is this plus here becomes a minus. So quite often derivatives of d1 and d2 are very similar to each other. They differ by a sign or not at all, depending on what you're taking the derivative with respect to. So in order to take a derivative of a function of several variables, we have to define a new concept called a partial derivative. So I have a function from Rn into R, and the partial derivative of f with respect to the jth input, I'm going to denote that as partial of f with respect to xj, and that's also going to be a function of n variables. And we're going to define the partial derivative then just to be this limit on the right-hand side. And if you look closely, all I'm doing is I'm treating everything except for x sub j as if it were a constant. So I'm leaving those the same. And then I'm using, just on the one variable I'm interested in, so x sub j, I'm going to use the definition of the derivative on that one particular piece. So I'll add h to that. And then I'll subtract our initial point. So this is the point where I'm trying to find the derivative. And then I'm going to divide by h, and then take the limit as h goes to 0. And then we say that this has a derivative if this limit exists and is finite. And in practice, the way we're going to compute these are we're just going to fix xk for every x that's not equal to j. So remember, I'm trying to compute the jth partial derivative. So I'm just going to treat xk, any other variable, as if it's a constant. And then just to differentiate f as if it were a function of one variable, and that one variable being xj. So for example, if I let my function, so I'm going to choose a function of two variables, and I have x squared y plus e to the minus xy cubed. And I want to take the derivative of this function now. I guess I should mention a little bit here about notation. So when we're taking a complete derivative, so if it's a function of one variable and I take its derivative, I've just been using d by dx. And when I'm taking a partial derivative, I use this funnier symbol that looks kind of like a twisty d, that I'm just going to read as partial. And so because this is a sum of two functions, I still have a linearity property. So I can, the derivative of a sum is the sum of the derivatives. So this is going to be equal to the derivative of the first term plus the derivative of the second term. And then to take the derivative of this piece here with respect to x, I'm going to make a substitution. So I'm going to say minus xy cubed. I'm going to call that u. I think that's what I decided to do. Yeah. So I can rewrite this like this. So if I look at what happened in the first term, since I'm taking the partial derivative with respect to x, my rule was treat y like it's a constant. So if y is a constant, I can use my formula that says c times x squared. The derivative of that is equal to c times the derivative of x squared. So in this case, now y is my constant, so I can just say that's equal to y times the derivative, y times the partial with respect to x of x squared. And then for the term on the right, I'm taking the partial derivative of a function of u. So a partial derivative with respect to x of a function of u, so I have to use the chain rule here. And so the chain rule says that the derivative of this is going to be the derivative of my function of u times the derivative of u with respect to x. So the derivative of e to the u is just e to the u, and then I still have to calculate this partial u partial x. And I'll do that just by taking the derivative of my substitution here with respect to x. And then for the first term, that was pretty easy. I just used the power rule to say that the derivative of x squared was 2x, so I end up with 2xy. So the partial derivative of my substitution with respect to x is just going to be minus y cubed. So that's just minus y cubed times x and using the power rule. And then I just have to reverse my substitution. So I'm going to replace this u right here with minus xy cubed. And I end up with 2xy minus y cubed times e to the minus xy cubed. So that was the derivative with respect to x. We can repeat now for the derivative with respect to y. So I'm going to set this up exactly the same way. Use the linearity property to write this as the sum of two derivatives. Make the same substitution. But this time, when I look at the first term, now I'm taking the derivative with respect to y, so it's the x squared I can bring out. So I have x squared times the partial with respect to y of just y. And then on the right-hand term, I have partial with respect to y of e to the u. So by the chain rule, I'm going to have to multiply the derivative of e to the u times partial u partial y. And again, I'm just going to take the derivative, but this time with respect to y of my substitution. So that gives me my chain rule derivative. So I have du dy equals minus 3 xy squared. So that's here just treating x as a constant and taking the derivative of minus y cubed using the power rule. And then I just have to plug everything back in, and I get the partial derivative of f of x with respect to y. And so essentially what we're going to have to do to get a full idea of what the derivative of f of x looks like is we need every partial derivative. And so if f is a function of n variables with one output, so the output is a real number, then I'm going to define something called the gradient of f, which is denoted sometimes by capital D times f of x. So here we think of capital D kind of the same way I think of d by dx. It's an operator, so it means take the gradient of the function f of x. And the gradient is just going to be an array of the partial derivatives of f of x. So each one of these terms, so each one of these elements of the array, df, dx1, or partial f, partial x1, that's a function of n variables. Partial f, partial x2, that's also a function of n variables. And then one last thing that we might have to deal with is a function of one or more variables that takes values in a multidimensional space is called a vector-valued function. And so in this case, what I'm after is I have, say, two inputs, and my function gives me two outputs. And so in this case, I'm going to use the function, the notation f from Rn into Rm. And so this just means that f is a function that takes n arguments. So there are n inputs to this function. And then there are m outputs to this function. And the way to think about this is you have f of my n inputs. I can have m different sort of sub-functions, each one of whom returns the element 1, 2, 3, up to m of the vector of outputs. And so in this case, when we try and make the gradient, we're going to have, instead of just an array that only has one row, we're going to have one row with n columns for each element of the output. So now my gradient is going to end up being an array with m rows and n columns. So there are n times n first-order partial derivatives, which is a lot to work with.